Okay, let's talk about joining charge capacitors. Now let's say you had the first capacitor, which is 300 millifarads, okay, and you connect it to a cell. So let's say you connect it to a cell of 12 volts. Okay, so when you connect this capacitor of 300 millifarad, maybe I write on top here. So 300 millifarad. So what will happen is this cell will charge the capacitor, right? So what will be the total charge dot? So the total charge dot in your capacitor will be Q equals to CV lah. So it will be 300 millifarad times 12 volts. So you get 3.6 coulombs lah. So this will be the charge dot in this capacitor lah. And what is the energy stored in this capacitor? So we can also use W equals to half QV or half CV squared, it doesn't matter. Now let's say we use W equals to half CV squared, so which is half times 300 millifarad times 12 squared. So what energy will we get? So you get 21.6 joules. Okay, so this is the first case. So then what happens is, when this capacitor is fully charged, what we will do is we will disconnect it from the battery. That means it has this charge and this energy, and we connect another uncharged capacitor of 100 millifarad. That means this second capacitor, 100 millifarad, is initially uncharged, is neutral. So when you do that, what will happen is the 300 millifarad capacitor will now charge the 100 millifarad capacitor. So we want to learn what's happening now. So what will happen is, we will figure out that the charge stored in both capacitors will still be the same. Now what do you mean by the same, right? Because you see, so the charge which is here, which is 3.6 coulomb, it will redistribute to this capacitor. So what do you mean by redistribute? Because remember, this is negative, this is positive, right? So that means when you connect this to a neutral capacitor, then the electrons will flow from lower potential to higher potential. It means from negative flow to neutral. So one electron will come here, another electron will be repelled, so this will become positive. Another electron come here, another electron will be repelled, so this also becomes more and more positive. This will become more and more negative. So as the charge flows from here to here, when will it stop flowing? It will only stop flowing when this potential equals to this potential, and this potential equals to this potential. That means the PD here equals to this PD lah. Now when that happens, you have just a redistribution of charge, because let's say you had 20 electrons here, 5 float here, you still have left with 15. So the total will still be 20. So the total charge must still be the same, no difference. So the total charge will still be the same as the charge dot in one of the capacitor just now, which is 3.6 coulomb. But what is the energy, what is the PD now? The PD when they stop flowing. Now you cannot say that because this is 12 volts, when you connect like this, then it will be 6 volts, 6 volts. It doesn't work like that. You have to find the new PD. To find the new PD, you already know the new total charge dot, which is the same as this, but you also need to know the new total capacitance. So the question is, when you connect like this, is this series or parallel? Because capacitors in series, the capacitance have a different formula than capacitors in parallel. So how do we know whether it's series or parallel? We actually look at the connections, like similar to your cell last time. If let's say you had a cell connected this way, alright, to another resistor, we will call this parallel or series, the two cells? Parallel. But if let's say you connect it like this, will it be series or parallel? Series. So how do we know? It's by connection of the terminals. If positive connect to negative, positive connect to negative is series. Positive to positive, negative to negative will be parallel. So in our case, we are connecting from negative to negative, positive to positive. Now you have no choice because the moment you connect this capacitor to this capacitor, then the electron will flow from the negative to here. So that means both will be negative. And then you will repel the electrons from here to here, so both will be positive. So it's not like you can choose, I want to connect them in series. The moment you connect an uncharged capacitor to a charged capacitor, they will distribute their charges, negative same side, positive same side, so therefore they will be in parallel. So anyway, so because they're connected in parallel, so their total capacitance is easy, you just add up both lah. So 300 millifarad plus 100 millifarad, so the total capacitance will be 400 millifarad. So what is the final PD? Remember the formula V is equals to Q over C. So you take the Q, which is 3.6 coulomb, divided by 400 millifarad, and you will get the final PD as 9 volts. That means after charging, both the capacitors will have 9 volts, not 6 volts. So what is the total energy stored now? So to find the total energy stored, we can use W equals to half CV squared. So you can use the half times the combined capacitance 400 milli times the final voltage 9 squared. And when you do that, you will get lesser the energy than before. You will get 16.2 joules. So even though your charge stored initially, which is 3.6 coulomb, final also same, but energy stored will be different. Your initial energy stored will be 21.6 joule, but your final energy stored will only be 16.2 joules. So why does this happen? Because during the charging from here to here, there will be a large current flowing initially, and that causes a large heating effect in your wires. We call it in the connecting leads. So that energy loss will be the difference between this and this. Now you can also use you can also find another thing. You can also find individually how much charge will be here, how much charge will be here after they reach 9 volts. If you want to do that, you can use the formula separately. So we use the formula Q1 equals to C1V. So your C1 will be 300 millifarad times 9 volts, and you get 2.7 coulomb. And the charge stored in your second capacitor will be C2V, which is 100 millifarad times 9 volts, which is 0.9 coulombs. If you notice, if I added up these two, I will get 3.6 coulomb. Alright, so that's how you do it.